Alright, today I've got a box, and I want to do math to know how heat diffuses in that box. So we're going to derive with Cartesian coordinates, the heat diffusion equation. So I've drawn out, my x direction is from left to right, my y direction is going from in to out, it's going into the board, my z direction is going from down to up. So if I want to measure what heat is doing in this box, first, I want to find how temperature varies by position within that box, and then I can use something called Fourier's law to get the heat flux for each of those directions to know how heat moves within the body. So the first thing I'm going to do is break up each section of this box into the smallest pieces we can measure. So if I break up each section in the x direction, I'll call each length dx. So a bunch of dx's that I cut this into. Now for each unit of height, I have a bunch of dz's that I cut this into. And we're going to measure each one of these small units. The same thing with y, I'll have a bunch of dy's that I cut this into. So if I look at the smallest possible box I can measure, I will have a cube. In each length will be dx, in each width going into the board will be dy, and each height will be dz for this cube. Now, if I want to talk about energy, and I'm interested in heat diffusion in this box, I'm going to say the energy stored in this box is equal to whatever energy goes in minus whatever energy leaves plus whatever energy is generated in this box. And I'm going to try to get this term in terms of heat flow for the box. So how do I start out? Well, energy storage. I'm going to write energy stored as a function of density, so how much mass is there in a volume, times specific heat capacity, how much energy can that volume actually store. Then I'm going to multiply that by the change in temperature with respect to the partial change in time for some volume. And I'm just going to call the volume dV for now. I don't know what the volume is yet. Now for energy generated, energy generated as just Q, dV. So heat in a volume. It's the heat that this volume is making. So now I'm interested in energy in and energy out. Well, I can write energy in would be heat going into this box. So the heat going in the x direction, going from left to right. If it's going in, that's positive, and I define the positive x direction to be on the right. So whatever's entering will be coming from the left. So I have qx coming in. And I'll say qx. Now, aside from just that direction, it could also be coming up. So I'll have qz, heat flow in the z direction, going up. Finally, heat could enter into the box. So I'll call that direction y, as I did before, and call that heat flow qy. So our energy in is qx plus qy plus qz, all of the energy coming in each direction. Now, energy output, I want to define in kind of the same terms. So I'm going to say that whatever's coming out of this box equals the energy that was coming in, so qx, plus how much it changed. So qx plus dx. Now I'll call same thing leaving in the y direction, that heat flow is qy plus dy, because it's the heat flow at a slightly farther out point on y. It started coming before, we're leaving coming after the dy. Same thing for dz, only it's going directly up now. So coming out of the box, we have qz plus dz. So if I want to write energy output, that's going to be equal to the sum of all of the energy flowing out, qx plus dx plus qy plus dy plus qz plus dz. Now, those are two kind of different terms. That makes it harder for me to do math. Luckily, I learned what a Taylor expansion was. So I'm going to make a Taylor expansion for each of these energy output terms. I have qx over here. I'm going to say that qx plus dx. I'm interested in the energy leaving and writing it in another cooler way. I'm going to write as the energy that was going in, so qx, plus however much that temperature changed by. So the change of qx respecting that position. Do the same thing for the y direction. Y plus dy is equal to that initial heat flow going in plus dy, dy, and finally same thing for the z direction. So I want energy leaving, writing it with a Taylor expansion, qz plus dz is equal to qz plus the change in that heat flow in the z direction, respecting the z direction. Now if we go back to our initial heat diffusion equation, we said that energy storage was equal to energy going in minus energy going out plus energy generated. I already like the term for energy generated and for energy storage. Those terms make me happy. But energy in and energy out looks like I can cancel now that I have these Taylor series expansions. So if I write energy going in minus energy going out, and I already did just the x direction, so I'll say for x is going to be equal to qx coming from here minus our Taylor series expansion for qx plus dx. So we said qx plus dx is equal to qx plus d qx dx. Wonderful. Now we notice that we have qx minus qx, so this can cancel. And if we distribute the negative, we have that only for the x direction still, energy input minus energy output is equal to the negative derivative of the heat flow in the x direction for each unit length x. So if I want to write our full energy storage times energy input equals energy input minus energy output plus energy generation, I can write that with the Taylor series expansion cancellation for each term. So just like before, energy storage is equal to density times specific heat capacity times the change in temperature, change in time. And before we had dV, well, we've been working with all of our dimensions for a little bit. What volume do you think we're talking about here? We're measuring a small cube, so the volume of a cube is length times width times height, or in this case, dx times dy times dz. So we said that's how long each of our unit length we were measuring by were. So I can rewrite dv as dx, dy, dz for energy storage is equal to energy input minus energy output plus energy generation. I'm going to write plus energy generation first. We said that was q dot dv. And similarly, I'm going to write dv as dx, dy, dz. And I'll even write it up here next to the term so it's a little bit more obvious. dv equals, for Cartesian coordinates, dx, dy, dz. Now we're adding energy input minus energy output. So we said for the x direction, energy input minus energy output was equal to negative derivative of the heat flow in the x direction over that unit length we're talking about, dx. Now I can actually do the same thing for each of the other directions. When you notice only the direction is changing, nothing else is changing for each of these terms. So I can say minus derivative of the heat flow in the y direction, respecting each unit y of length, minus partial derivative of the heat flow in the z direction, respecting each z unit of length. This is looking closer to an equation that I like. However, we have Fourier's law that gives us a better way to write heat flux. So we have heat flux, that's the Q with 2 dashes on it, is equal to negative thermal conductivity times the derivative of temperature for each unit length. Now, if I want to make that a heat flow instead of a heat flux, once again, I have to multiply by the area that it's going through. So, in the x direction, I'll use Fourier's law. And say the heat flow in the x direction, Qx, is equal to negative k times what area is x going through? Well, I said x was from left to right. So if x is going from left to right in my cube, then I need to go through an area that is normal to that. So this side area. It looks like it has a side length of dy and a height of dz. So the area that heat flow is going through is dy dz. Multiply that by partial derivative of temperature, respecting, in this case, our unit length is dx, so dt dx. I can do the same thing for the heat flow in the y direction. It's equal to negative k. What plane is the y direction going to? So y was going into the whiteboard, so it's breaking this front face of the cube that I have with a length of dx and a height of dz. Let's say dx dz. And then same as before in Fourier's law, we have derivative of temperature respecting what direction we're talking about. So in this case, partial derivative of temperature, partial derivative of y direction. Finally, I can do the same thing in the z direction. Z is going up, we said, so from down to up, we're going across dx, dy, like that face in here. So each side length is dx, each width is a dy, dx, y, and same as before, but with z. So now going back to our big heat diffusion equation over here, we have a whole new way to write the heat flow in each direction. So let's do it. We have energy storage, PCP, density times specific heat capacity, partial derivative, temperature respecting time, dx, dy, dz is equal to q dot dx, dy, dz times, now I have the negative derivative of the heat flow. So this negative sign will distribute. You notice that our Fourier's law expression of heat flow is also negative. So if I bring in and I'm trying to write Qx in a new way in this term, that negative will cancel out. So I can say plus the partial derivative of respecting x. Now before we just had Qx and it was negative, now we have positive. So I'll write k dy dz dt, derivative of temperature, derivative in the x direction. Now, just like before, we had dx at the end, right? Dx at the end. So that's our full expression for heat flow in the x direction. The same thing with y, negatives cancel out. I have the derivative, partial derivative, y, of our expanded with Fourier's law, k times the plane it goes through, dx dz, times partial derivative of temperature in the y direction and dy. Finally, same thing in the z direction, plus partial derivative of qz, and in parentheses I'm writing our new way to write qz, which is k times the plane it goes through, dx dy, of change in temperature, change in the z direction, dz. So this whole thing is our heat diffusion equation. However, it looks like I have a dy dx dz over here, a dy dx dz in my energy generated term. If I distribute, I have a dy dx dz, my x term, and I have one in every term. I can finally cancel that out and write my heat diffusion equation a lot cleaner and say density times specific heat capacity of our material, and that just gives us our thermal energy that's happening there. When we multiply energy by specific heat capacity, that's our thermal energy term, times change in temperature, change in time, equals q dot, so our energy generation term, plus our directional energy going in minus energy going out, with the volumes canceled out. So we have d dx, those are partial derivatives of k dt dx. Now notice we don't have that dx on the end anymore, because we combined it with the dy dz and canceled out our volume term. So it's just d dx k dt dx. Do the same thing in the y direction. Partial derivative, y direction, k t d y, and finally in the z direction, and that gives us our final heat diffusion equation for Cartesian coordinates. Move away to make sure that you can see it in the recording. Maybe even bring the camera up at the end so you can get a good look at everything that's happening. Thank you for watching.